Calculus is a fascinating branch of mathematics. It primarily deals with continuous change. Think of it as a special lens. This lens allows us to look closely at how things change from one moment to the next. If algebra helps us solve for unknowns in static situations, calculus helps us understand systems that are in motion or evolving. It provides tools to analyze rates of change and accumulation. This ability to quantify and predict change is incredibly powerful. Many natural phenomena involve continuous change, making calculus essential for understanding them. So calculus is fundamentally the study of how quantities change. Imagine you have a very powerful microscope. This microscope is not for looking at tiny cells. Instead, it is for examining mathematical functions and geometric shapes in minute detail. Calculus acts like this mathematical microscope. It allows us to zoom in on a curve until it looks almost like a straight line. It helps us see how a function behaves at an infinitesimally small interval. This zooming in process is key to understanding concepts like instantaneous speed or the precise slope of a curve at a single point. This microscopic view reveals hidden properties and relationships that are not apparent with simpler mathematical tools. Calculus is broadly divided into two main branches. These branches are differential calculus and integral calculus. Differential calculus focuses on rates of change. It helps us find how quickly something is changing at a specific instant. For example, it can determine the speed of a car at a particular moment. Integral calculus, on the other hand, deals with accumulation. It helps us find a total amount when the rate of accumulation is known. For example, it can calculate the total distance a car travels if we know its speed over time. These two branches are deeply connected. The development of calculus in the late 17th century, primarily by Isaac Newton and Gottfried Wilhelm Leibniz, was a monumental achievement. It marked a turning point in the history of science and mathematics. Calculus provided the language and tools necessary to describe the physical world with unprecedented accuracy. It enabled the formulation of laws of motion and universal gravitation. This, in turn, fueled the scientific revolution and paved the way for countless technological advancements. Its invention revolutionized how we approach problems involving change and motion, a legacy that continues to shape our world today in profound ways. The importance of calculus extends far beyond the walls of academic institutions. It is not merely a subject for mathematicians and scientists. Its principles and techniques are applied in a vast array of fields. Understanding calculus opens doors to comprehending the mechanics of the world around us, from the trajectory of a thrown ball to the complex interactions within an ecosystem. Calculus provides a framework for analysis. It empowers us to model, predict, and optimize systems in diverse areas. This makes it an indispensable tool for innovation and problem-solving in the modern age, influencing decisions and designs we encounter daily. In the realm of physics, calculus is absolutely fundamental. Sir Isaac Newton, one of its co-inventors, developed calculus to help explain his laws of motion and universal gravitation. For instance, to describe how the velocity of a falling object changes due to gravity, we use derivatives. To calculate the work done by a variable force, we use integrals. Concepts like acceleration, momentum, energy, and electromagnetic fields are all expressed and manipulated using the language of calculus. Without it, modern physics as we know it, from classical mechanics to quantum theory, would simply not exist. Engineers of all disciplines rely heavily on calculus. Civil engineers use it to design safe and stable structures like bridges and dams, calculating stresses and loads. Electrical engineers apply calculus to design circuits, analyze signals, and understand electromagnetic waves. Mechanical engineers use it to design engines, vehicles, and machines, optimizing their performance and efficiency. Aerospace engineers use calculus to calculate rocket trajectories and spacecraft orbits. The precision and predictive power offered by calculus are crucial for ensuring the functionality and safety of engineered systems that society depends upon. Even in fields like economics and finance, calculus plays a surprisingly significant role. Economists use derivatives to determine marginal cost and marginal revenue. This helps businesses make optimal production decisions to maximize profit. Financial analysts use calculus concepts in risk management and to model the behavior of financial markets. For instance, the Black-Scholes model for option pricing involves calculus. Biologists use calculus to model population growth, the spread of diseases, or the rate of chemical reactions within organisms. The reach of calculus is truly extensive, showing its versatility and fundamental nature. The concept of a limit is one of the most fundamental ideas in all of calculus. It forms the bedrock upon which both differential and integral calculus are built. In simple terms, a limit describes the value that a function approaches as its input or variable gets closer and closer to a certain number. It's not necessarily about what happens at that number, but rather the behavior of the function in the immediate vicinity of that number. Understanding limits is crucial because it allows us to deal with situations where direct evaluation might be impossible or undefined, such as division by zero. Imagine you are walking towards a wall. With each step, you get closer to the wall. Your distance to the wall approaches zero. Even if you never actually touch the wall, we can talk about the limit of your distance to the wall as you continue walking towards it. Similarly, in mathematics, we might examine a function f(x). As x gets progressively nearer to a value, say c, the limit is the value L that f(x) gets arbitrarily close to. This idea of getting arbitrarily close is central. It allows us to define continuity and the instantaneous rate of change with precision. Why are limits so important? They are the formal tool used to define continuity. A function is continuous at a point if its limit at that point exists. The function value at that point exists, and these two are equal. More significantly, limits are essential for defining derivatives. A derivative, which measures an instantaneous rate of change, is defined as the limit of an average rate of change as the interval over which the average is taken becomes infinitesimally small. Without limits, the entire structure of calculus would lack its rigorous foundation. They allow us to handle the concept of infinity and infinitesimals in a precise mathematical way. The notation for a limit is quite straightforward. We write lim f(x) as x approaches c equals L. This is read as the limit of f(x) as x approaches c equals L. Evaluating limits can sometimes be as simple as substituting the value c is into the function f(x). However, in many important cases, especially when this substitution leads to an undefined expression like 0 over 0, more sophisticated techniques are required. These techniques might involve algebraic manipulation, using known properties of limits, or applying special theorems. The core idea, however, remains: what value does the function trend towards? The concept of limits, while abstract, finds echoes in various real-world phenomena and historical problems. Consider Zeno's paradox of Achilles and the tortoise. Achilles, being much faster, gives the tortoise a head start in a race. Zeno argued that Achilles could never overtake the tortoise. By the time Achilles reaches the tortoise's starting point, the tortoise has moved a little further. When Achilles covers that new distance, the tortoise has moved again, and so on. This creates an infinite sequence of smaller and smaller distances. While practically Achilles does win, the paradox highlights an early engagement with the idea of an infinite process and an approaching limit. Another practical illustration of limits can be seen in how we approximate the properties of curved shapes. For instance, to find the circumference or area of a circle, ancient mathematicians like Archimedes used polygons. They inscribed and circumscribed polygons with increasing numbers of sides around the circle. As the number of sides of the polygon increases, the polygon's perimeter gets closer and closer to the circle's circumference. The limit of the perimeters of these polygons, as the number of sides approaches infinity, is precisely the circumference of the circle. This method of exhaustion is a precursor to integral calculus, heavily reliant on the idea of a limit. Think about a skydiver jumping from an airplane. Initially, their speed increases rapidly due to gravity. However, as their speed increases, so does the air resistance acting against them. Eventually, the force of air resistance becomes equal to the force of gravity. At this point, the net force on the skydiver becomes zero, and they stop accelerating. They reach a constant speed called terminal velocity. This terminal velocity can be thought of as a limit. It's the speed the skydiver approaches as time goes on, even if they theoretically never perfectly reach it in a finite time due to minute fluctuations. In our digital world, limits have a conceptual connection to how continuous information is represented. For example, digital audio is created by sampling an analog sound wave at discrete time intervals. The more samples taken per second or higher sampling rate, the closer the digital representation is to the original continuous sound wave. Similarly, a digital image is made of pixels. As the number of pixels increases or higher resolution, the image appears smoother and more like the continuous reality it represents. While not a direct mathematical limit, it illustrates the idea of approaching a continuous reality through increasingly finer, discrete approximations, a core theme in calculus. Section 5. Instantaneous change. The power of derivatives. After understanding limits, we can explore one of the central concepts of calculus, the derivative. The derivative of a function measures its instantaneous rate of change at a specific point. Imagine driving a car. Your speedometer shows your instantaneous speed, how fast you're going at that very moment. This is precisely what a derivative can tell us about any function that describes a changing quantity. If a function represents the position of an object over time, its derivative with respect to time gives the object's velocity. If the function represents a company's profit versus its production level, the derivative indicates how profit changes with a small increase in production. Geometrically, the derivative has a very clear interpretation. It represents the slope of the tangent line to the graph of the function at a particular point. A tangent line is a straight line that just touches the curve at that point, matching its direction there. Think of a winding road on a map. At any point on that road, you can imagine a straight line segment that indicates the road's direction at that exact spot. The steepness of this segment is analogous to the derivative. If the curve is rising, the derivative is positive. If it's falling, the derivative is negative. If it's flat, the derivative is zero. The formal definition of a derivative relies directly on the concept of limits. To find the instantaneous rate of change, we first consider an average rate of change over a very small interval. Let's say we have a function f of x. The average rate of change between x and x plus h, where h is a small change in x, is given by f of x plus h minus f of x, all divided by h. This is the slope of a secant line connecting 2 points on the curve. To find the instantaneous rate of change, or the slope of the tangent line, we take the limit of this expression as h approaches 0. This limit, if it exists, is the derivative of f of x. Once we understand the definition, we can develop rules for finding derivatives more easily without always going back to the limit definition. These are called differentiation rules. For example, the power rule tells us how to differentiate functions like x squared, x cubed, and so on. The derivative of x to the n is n times x to the n minus 1. The derivative of a constant is always 0 because a constant value does not change. There are also rules for sums, differences, products, and quotients of functions. These rules are the workhorses of differential calculus, allowing us to efficiently calculate rates of change for a wide variety of mathematical models. Section 6. Derivatives in action modeling our dynamic world. Derivatives are not just abstract mathematical tools, they are incredibly useful for modeling and understanding our dynamic world. One of the most direct applications is in physics, particularly in the study of motion. If you have an equation describing the position of an object over time, taking the first derivative of this equation with respect to time gives you the object's instantaneous velocity. Taking the derivative again, the second derivative gives you its instantaneous acceleration. This allows physicists and engineers to precisely analyze how objects move, from planets orbiting stars to cars on a highway. In the world of business and economics, derivatives are used for optimization. Companies often want to maximize their profit or minimize their costs. If a function describes the profit of a company based on the number of units it produces, the derivative of this profit function can help find the production level that yields the maximum profit. This occurs where the rate of change of profit, the derivative, is 0, often indicating a peak or valley in the profit curve. Similarly, derivatives can help find the most efficient way to use resources or the minimum amount of material needed for a construction project. Medicine and biology also benefit greatly from the application of derivatives. For instance, doctors might want to understand how quickly the concentration of a drug in a patient's bloodstream is changing over time. This rate of change can be found using derivatives, helping to determine optimal dosing schedules. Biologists use derivatives to model population growth rates, the spread of epidemics, or the rate at which a tumor is growing or shrinking in response to treatment. Understanding these rates of change is crucial for making informed decisions in healthcare and ecological management. Beyond these specific examples, derivatives are fundamental in many scientific and engineering disciplines for analyzing any system where quantities are changing. They help in understanding fluid flow, heat transfer, and chemical reaction rates, and the decay of radioactive substances. For example, the rate at which a hot object cools down can be modeled using differential equations, which involve derivatives. The ability to quantify and predict rates of change allows for better design, control, and understanding of complex systems all around us, making derivatives a cornerstone of modern science and technology. Section 7. Accumulating change, the essence of integrals. While differential calculus focuses on breaking things down to understand instantaneous rates of change, integral calculus does the opposite. It is concerned with accumulation, with summing up quantities. If you know how fast something is changing, its rate integration can help you determine how much of it has accumulated over a certain period or interval. Think of it as the process of putting together infinitely many tiny pieces to find a whole. For example, if you know the velocity of a car at every moment in time, integration can tell you the total distance it has traveled. Geometrically, one of the most common interpretations of a definite integral is the area under the curve of a function. Imagine you have a graph of a function, say x, between 2 points A and B on the x-axis. The definite integral of fx from A to B represents the exact area enclosed between the curve, the x-axis, and the vertical lines x equals sine A and x equals sine B. This might seem like a purely geometric problem, but it has vast applications. Many real-world quantities can be represented as areas under curves, such as total work done by a variable force or total consumption of a resource over time. There are two main types of integrals: definite integrals and indefinite integrals. A definite integral, as mentioned, calculates a specific numerical value, often representing an area or a total accumulation over a defined interval, a, b. An indefinite integral, also known as an antiderivative, is a function whose derivative is the original function. If fx equals sine fx, then fx is an indefinite integral of fx. It represents a family of functions, all differing by a constant, because the derivative of a constant is zero. The indefinite integral provides a general solution before specific limits of integration are applied. The true power and elegance of calculus are revealed in the fundamental theorem of calculus. This theorem establishes a profound connection between differentiation and integration. It essentially states that these two operations are inverses of each other, much like addition and subtraction, or multiplication and division. Part 1 of the theorem shows how to calculate a definite integral using an antiderivative. Part 2 shows that the derivative of an integral of a function returns the original function. This theorem provides a powerful method for evaluating definite integrals without resorting to the cumbersome process of summing an infinite number of tiny rectangles. Section 8. Integrals at play from areas to totals. The applications of integrals are incredibly diverse and extend to numerous fields, often mirroring the applications of derivatives, but from an accumulative perspective. One of the most intuitive uses is calculating the area of irregular shapes. While we have simple formulas for areas of rectangles, triangles, and circles, many shapes in the real world are not so straightforward. If we can describe the boundary of a shape with a function, integration allows us to find its precise area. This is useful in fields like architecture for land surveying or in manufacturing for determining material quantities. Another common application is finding the total distance traveled by an object when its velocity is known, but not constant. If you have a function representing the velocity of a car over a period of time, integrating this velocity function with respect to time over that interval will give you the total displacement or distance the car has covered. This is because velocity is the rate of change of position, and integration sums up all the small changes in position to give the total change. This principle is vital in navigation, aerospace engineering, and any field involving motion analysis. Integrals are also indispensable for calculating the volumes of solids, especially those with curved surfaces or irregular shapes. Techniques like the disk method, washer method, or method of cylindrical shells use integration to sum up an infinite number of infinitesimally thin cross-sections of a solid to find its total volume. This is crucial in engineering for designing containers, machine parts, or even in medicine for calculating the volume of organs or tumors from medical scans. The ability to precisely determine volumes is fundamental for many design and manufacturing processes. In economics, integrals are used to calculate concepts like total consumer surplus or producer surplus. Consumer surplus represents the total benefit consumers receive when they pay less for a good than what they were willing to pay. Producer surplus is the total benefit producers receive when they sell a good for more than their minimum acceptable price. These quantities can be represented as areas between demand and supply curves and the price level, and these areas are calculated using definite integrals. This helps economists understand market efficiency and the welfare effects of different policies. Section 9. Your calculus journey. The adventure begins. We have journeyed through the foundational concepts of calculus. We started by understanding that calculus is the mathematics of continuous change. It helps us analyze how things evolve and accumulate. We then explored the three core pillars: limits, derivatives, and integrals. Limits provide the rigorous foundation describing how functions behave as inputs approach certain values. Derivatives give us the power to find instantaneous rates of change, like the slope of a curve at a point. Integrals allow us to accumulate quantities, such as finding the area under a curve or the total change from a known rate. Throughout this exploration, we've seen that calculus is far more than just a collection of abstract rules and formulas. It is a powerful tool with pervasive influence across science, engineering, economics, medicine, and many other disciplines. From designing safer bridges and more efficient engines, to modeling financial markets and understanding biological processes, calculus provides the essential language and methods. Its ability to model dynamic systems and solve problems involving change makes it one of the most significant intellectual achievements in human history, shaping our modern technological world in countless ways. Mastering calculus, like any significant skill, requires perseverance and consistent practice. The concepts can seem challenging at first, but with dedicated effort, they become increasingly intuitive. Work through examples, try to visualize the geometric interpretations, and always ask why a particular method works. Don't be discouraged by mistakes. They are an integral part of the learning process. Each problem solved and each concept understood builds a stronger foundation for tackling more complex ideas. The beauty of calculus often reveals itself gradually as you begin to see its interconnectedness and its power to describe the world. This introduction is merely the first step on a longer, rewarding journey into the world of calculus. There are many more fascinating topics to explore, such as sequences and series, multivariable calculus, differential equations, and vector calculus. Each of these builds upon the fundamental ideas we have discussed. We encourage you to continue your exploration, whether through further coursework, textbooks, or online resources. The path of learning calculus is an adventure that sharpens your analytical thinking and problem-solving skills, opening up new perspectives on the intricate patterns and processes that govern our universe.